All right, so last time we talked about an example. We worked through an example where we worked out a line integral with respect to x, and then with respect to y. We combined two types of line integral in one problem. We've been looking so far at line integrals over curves that live in the xy plane. So line integrals over two-dimensional curves of functions of two variables. And so in this video, we're going to generalize a little bit, and we're going to consider now curves that live in three space. So not just two-dimensional curves, three-dimensional curves. C can be three-dimensional now. And we're also going to consider functions of three variables now, instead of just functions of two variables. And so don't think of these as new kinds of line integrals. These are almost identical to what we've been doing. You just have a third variable involved, and of course C is no longer flat. So we can talk about the line integral. I shorten this. Really, it's the line integral of f along C with respect to arc length. I abbreviate to just with respect to arc length. It's exactly the same definition you saw before, the integral from a to b of f of r of t times the length of r prime of t dt. So really good news. This isn't some new formula. It's the same formula, actually. It's identical. The only difference is there wasn't a z before, and now there is. Same things for line integrals with respect to x. Your dx becomes x prime dt, dy becomes y prime dt, dz becomes z prime dt. So we can, I think I've actually got that copied on my clipboard. Whoops, I've got the equal sign there though, so let's get rid of that. And then for this one, you just get f of r of t times x prime of t dt. For this one, you're going to get same thing, f of r of t, but then you're going to multiply by y prime of t dt. And then for the bottom one, you're going to get, whoops, let's slide that up. You're going to multiply by z prime of t dt. So again, these two definitions right here, these two integrals, are exactly the same as you saw before. The difference is there wasn't a z, and then of course the last one is exactly what you'd expect. So I thought we'd do one example of this just to make sure that we're comfortable. And here we go. So I wanted to work out this particular line integral. So here's my function of three variables, and then I'm telling you C is actually, it's a line segment. It's just this little piece of line. You can sketch it if you want to. I don't feel the need to sketch this. I know what a line looks like, and there's really not, it's not going to be helpful to me. I do need to parameterize this. And so let's keep in mind when you want to parameterize a line segment, you want to find the direction vector. We're starting here, going there, so we're going to say for our direction vector v, we're going to say head minus tail. So we're going to say 1 minus 0, 6 minus 0, 4 minus 0. Well, that's easy. We just get 1, 6, 4 as our direction vector. And then so r of t is your starting point, which is just 0, 0, 0 plus t times your direction vector, and you just end up with t, 6t, and 4t. And of course you need to know the bounds on t, which those are just 0 to 1. I encourage you, when you work out a parameterizing a line segment, it's always good to plug in the beginning point and make sure you end up where you want to be, 0, 0, 0, plug in 1, I'm at 1, 6, 4, so this seems to work out perfectly, and it should, because it's correct. Okay, so we've got our parameterization. Whoops, that's not what I wanted. Now we need to go ahead and work out the integral. So I know that the formula, remember the formula with respect to arc length, I know that ds is going to become the length of r prime dt. So I better compute r prime. I'll erase that. I'm going to compute r prime. And it shouldn't surprise you one bit. When you compute r prime, you're just taking the derivative with respect to t of each component. You're just going to get 1, 6, and 4. You just get the direction vector, which is 1, 6, and 4. And now we can compute the length of r prime. And you're going to get what? Let's see. 1 squared is 1, 36, and 16. So this should be the square root of 53, I believe. Yeah. So square root of 53. So, okay, we're ready to go. So now we can copy our original problem. If you're writing it by hand, I would encourage you to rewrite it There's just something nice about doing mathematics in a pretty sort of way. Keep it all nice and neat and tidy as best you can. All right, so all I'm going to do now is I'm going to take my r of t and I'm going to plug this component in for x, this component in for y, and this component in for z, and then I'm going to multiply by the length of r prime of t dt. So let's just go real slow here. The integral is going to go from 0 to 1. That's coming from the bounds on t. X becomes t e to the yz. Y is 6t. Z is 4t. You multiply by length of r prime is root 53 dt. Of course, you're going to clean this up a little bit and write this as the square root of 53 integral 0 to 1 of t e to the 24t squared dt. At this point in your careers, I fully expect you to be able to handle this integral without even batting an eye. This is just a basic u sub. Let's write down what u should be. So u is going to be 24t squared dt. 24t squared. du is going to be what? 48t dt. You're going to end up with an integral of e to the u du, and you should get square root of 53 over 48 times e to the 24th minus 1. So I would encourage you to pause the video and work that out yourself. Make sure that you can get it. I'm going to stop the video right here, and we'll pick up in the next one with our last kind of line integral.